Okay, in this problem here we're asked to get the most area. We're told a farmer has 250 feet of fencing and he wishes to construct a rectangular fence with one side open to the river. What dimensions will give the most area? Well, we can begin by drawing a picture. So there's our river and there's our fence, and one side again is open to the river. So we can label the sides of our fence. We have X and Y. And so we want to optimize the area. So the first thing we want to do is write an equation involving area. We know for a rectangle, area is equal to X times Y. This equation here is our primary equation. We say it's our primary equation because it contains the quantity that we want to optimize. In this case being the area. But as we look at this equation, we say, well, it has two variables, both an X and a Y. And so, well, we really don't want that. We need to have just one variable. So as we read through our problem, excuse me there, we know that the perimeter is 250 feet. And so we can relate X and Y by the perimeter. 2X plus Y would be equal to 250. That gives us an equation relating X and Y. And now we can solve that equation for one of the variables. And we do just that. From this point now, we can go on and say, okay, we solved for one of the variables, so now we can substitute that back in to our area equation. Our area equation now will tell us the area. And so we do just that. We go into that equation, replace the y with 250 minus 2x, and now we have an equation relating the area to just one variable, x. And we can set about trying to optimize. First though, a little bit of simplifying. And we were just ready to optimize, and the stupid purple blob came up and said, wait! Does x have any limitations? In an optimization problem, we always have to consider the possibility that there are limits, physical limits on what x can be. We only have 250 feet of fencing to use. So there's going to be a limited amount that we can assign to the side x. Because we know that if we're going to have a rectangle, both x and y have to be greater than 0. Well, we can easily say, okay, well, let's make x greater than 0. But then y is 250 minus 2x, and that also has to be greater than 0. Solving that inequality tells us that x has to also be less than 125. So x is stuck between 0 and 125. You won't always get definite constraints on both sides, but you should always at least have a constraint on one side that we can kind of work with. So now we want to optimize the function a equals 250 minus 2x squared, and we're optimizing it over the interval 0 to 125. Okay, so again, just saying what I just said. Stupid yellow blob. Now, we can do that by taking the derivative. So we get a equals 250 minus 4x. And then remember, to optimize, we want to know when the derivative is 0 or undefined. So we can set it equal to 0 because it's a polynomial. So it'll never be undefined. From which we get x is 62.5. Now at this point, we're optimizing over that interval. So we need to take now and evaluate our function at the endpoints and at 62.5 to see which, if any of those, which of those leads to the maximum value. So I've just rewritten my function, and now if I evaluate at 0, I get 0. If I evaluate at 125, I get 0. So basically we don't have a rectangle anymore. And then we evaluate at 62.5. We evaluate at 62.5, we get that it is 7,812.5 square feet. So that's going to be the optimal area, but that's not what our problem was asking about. Our problem was asking about the dimensions. So we now know that x is 62.5, and then we can plug in 62.5 in for x to figure out that y is 125. So the dimensions to get the absolute most area to house your livestock or whatever it is you're putting in this fence is 62.5 by 125. Okay, hopefully this helps you out with your optimization problems. Until next time.